Welcome to the AIAA Space Resources webinar series intended for education and outreach. Today, I'm very excited to host Mr. Robert Mueller from NASA Kennedy Space Center Swamp Works. I'll let him do a bit more intro of himself in just a moment, but before I let him launch into his slides and everything, I wanted to mention that we're still doing a space resources evaluation survey. We're trying to compile information from subject matter experts as part of the AIAA Space Resources Technical Committee, the same committee that hosts these organizations. So I just sent the message in the chat. If you guys would be so kind to fill that out, if you haven't already, we would really appreciate it. George Lordos is running that, and I'm sure he'd appreciate your input. We as a group do too. So without further ado, I'll hand it over to you, Rob. Take it away.
Okay, thank you very much, Jared. Hello, everybody. I'm going to share my slides. Can you see my slides?
Yes, we're all good here.
And you can hear me fine?
I can.
Okay, great. Well, thank you very much for attending. I'd like to give an overview of what it takes to do functional planning for construction of a lunar base, and that's what we're in the middle of doing here at NASA. And this will be an overview talk, and it's meant to stimulate thought. It's not meant to provide the answers. It's just meant to give you some insight into the process that NASA is using to plan for a lunar base. Some may call it different things, a state research station or an outpost. It doesn't really matter. It's a permanent human presence on the moon. That's what our goal is. I'll talk about the Artemis program, then dive into architecture and systems engineering, the Moon to Mars objectives, and some official documents that are publicly available to everybody. Envision futures for ECO, which is excavation, construction, and outfitting. Then we'll talk about a framework for lunar base construction and a work breakdown structure that we're using inside NASA. Some functional areas, a discussion on master planning and zoning, and we'll dive into the types of equipment needed, industry collaboration, the translation between the construction industry on Earth and the space industry, where we aim to do construction, and then finally a little discussion about mega projects on Earth and in space. I'm going to be going pretty fast. I have a lot of slides to go through. We'll do some Q&A at the end, but I will be going very fast. So just hang on, please. Just a quick background by myself. Mechanical engineer by training. I have a master's in space system engineering and MBA. I'm the former chairman of the American Society of Civil Engineers Aerospace Division. I'm also in the Space Resources Technical Committee for the AIAA, and this activity is a Space Resources TC activity. At NASA, I work at Kennedy Space Center, and I work as a senior technologist and principal investigators. I've worked at Kennedy Space Center, I've worked at Johnson Space Center, I've worked at Jet Propulsion Lab in my career. I've been at NASA for 34 years. I've worked on a variety of programs at NASA, but the last 15 years of my career I've focused on research and technology development, which is what I really enjoy to do. And I'm the co-founder of the Swamp Works Innovation Environment and the Granular Mechanics and Regolith Operations Lab. In my personal life, I'm a surfer, sailor. I fly UAV. I'm a licensed pilot for UAVs. Love to explore. I love to innovate, and I'm generally a student of life. So, of course, NASA has done amazing things over the last 60 years, starting with the Freedom 7 project there, the Mercury program, then the NASA Gemini program, Apollo program, Skylab, Space Shuttle, International Space Station, and now the latest big program that NASA is doing is the Artemis program. And you know, we've had a variety of very successful missions to the moon that are listed there, and the Mars program has been outstanding. And so nobody can argue with the success that NASA has had over the last 60 years. And we really want to continue that success and lead the next generation on to the moon and beyond, to Mars, and then even further beyond Mars to the asteroid belt and beyond. So Artemis does have this immediate goal in phase 1 of landing at the lunar South Pole. And Paul Sputus was a big advocate of landing at the South Pole or the North Pole. And the reason why is because the resources there, it's expected that we'll find water, ice resources at the poles, so it's a strategically important location. Now, this is not unique to the United States. This is actually a slide from the ISEG, the International Space Exploration Coordination Group, and you can see that there's just a lot of activity that you'll see in the next 10 years. The next 10 years are going to be very exciting, starting with Eclipse program, and we already have an Indian lander coming up in the next few months this summer. And we then will have the human landing system from the Artemis program, NASA Artemis program. So it's going to get very exciting, and that's why we're preparing now internally at NASA. We're very busy, and I don't think it's completely hit the public consciousness yet, but it will soon. Then after the phase one is all about proving that we can get the astronauts to the moon and land them safely, survive, come home. Then we start thinking about Mars forward capabilities, sustainable lunar presence. Now, you may ask yourself, how did NASA do this? How did NASA do all these amazing programs over the last 60 years? And how are we going to do Artemis? Well, if you're on the inside at NASA, there's something called NASA Systems Engineering Handbook. And almost everything at NASA follows this. Anything that's technical, really, unless it's science driven, if it's engineering driven, then it usually has a systems engineering component to it. And it's very important because it gives us a framework on how to do highly complex projects. The International Space Station, the Space Shuttle, Apollo program, arguably these are some of the most advanced and sophisticated engineering projects ever undertaken by humanity. So how did we do this? How is this possible? Well, the answer is systems engineering. And so the systems engineering process is in the handbook. It's available online. Anybody can go download it. And it walks you through the process of what it takes to do systems engineering for a very highly complex and sophisticated project. Now here you'll see these big blocks: stakeholder expectations, requirements definitions, design solution definition, logical decomposition. This is the secret sauce of NASA systems engineering right here on this slide. If this is followed well, then the project should be successful. And it begins with establishing needs, goals, and objectives, stakeholder expectations. Really need to get that very, very clear up front. What are the needs, goals, and objectives? If that's not clear, then the rest will not work because it's a flow down process. And you decompose all those needs, goals, and objectives into requirements and further into functional requirements, then technical requirements. And then what you'll notice is there's a lot of feedback loops here, a lot of iteration. So this is an iterative process. Now, if you dive further in, this whole process here is called stakeholder expectations definition process. It's just about finding out what are our needs and objectives. And that includes all the stakeholders. So just that alone is a big exercise. Next, you dive into the technical requirements definition process. So once you understand what you're trying to do, then you start to try to quantify it and put hard requirements on it so we can actually go design the equipment and make the missions happen. So this is a very well-known process, and engineers at NASA are well versed in the art of systems engineering. So what's important to understand is that we're in a big process here for going to the moon, and we're following the NASA systems engineering process. We're currently at the mission objectives phase where the stakeholders have their goals and objectives evaluated, and we have an iterative process until everybody's happy. Once all the stakeholders are happy, we go down to mission requirements, programmatics, and the functional requirements, and that's the master planning phase. So in the master planning phase, that's really where we start to design the moon base, and we're not there yet. And then later on, we have system performance requirements, and then we decompose those into functional performance requirements for the subsystems, derived requirements, and so on. So that's where we want to be, most of us. We want to be designing equipment and moon bases and systems and all that kind of thing. But we're not there yet. We're still at the master, we're not even at the master planning phase. We're still here at the mission objectives phase. And I'll dive into that a little bit more. So this is not the first time that NASA has tried to do this. We've been doing studies since at least 1988 and probably before that. in the 1950s and 1960s under Wernher von Braun and others, and even before Wernher von Braun. There have been many studies done. Arguably, Jules Verne was one of the first ones. However, at NASA, this has been heavily studied over the years, and you can see a list of the studies here. The latest one is the Artemis program, and the Artemis program really started with Space Policy Directive 1 in December 2017. And then we had permission from the National Space Council, Space Priorities Framework, NASA Strategic Plan. So you can see that this official process just takes a long time to work its way through the system. But if you look at it from a big picture point of view, that's all part of the stakeholders' objectives definition, goals and objectives definition. So that's where we are, but you can see we're making progress. Now, recently, in 2022, NASA released the Moon to Mars Strategy and Objectives. So now we have an official document that's publicly available at this website, and it focuses on the goals and objectives for science, transportation, habitation, lunar and Mars infrastructure, operations. And if you add all those goals and objectives together, then that's when you can start to formulate an architecture. And NASA is doing this right now, and they have annual architecture concept reviews. So that's how it's working. For this community here, we're particularly interested in the lunar and Mars infrastructure. And of course, the other ones are also interesting, but I think that's the one that this community is most interested in. Once we have the Moon to Mars objectives, then internally at NASA, we have the characteristics and needs, and those are allocated to different functional areas. And those are then allocated to the gray boxes, which is the NASA mission directorates. Each mission directorate has a different charter, a different purpose for existing, and STMD, the Space Technology Missions Directorate. So that's where the technologies get developed. And that's primarily where I work, because we're working on future technologies that don't exist yet. Now, it's very important to get the vocabulary, the terminology, vernacular right. And so here are the definitions. This is a definition of what objectives and goals are. Then you can have characteristics and needs, and then those go into sub-architectures where you can divide it up into functions, and then those functions become elements with requirements associated with them. And then the segments are the use cases. So these are more ConOps. So this is how you use the equipment, and this is what the equipment is. So keep those words in mind: architecture, sub-architectures, and segments. That's how NASA is structuring this. So then, if in systems engineering, a good systems engineering design has the end state. You start with the end state. What are you trying to do? What is exactly the goal here? So that's why we start with the end state here, till we go to the objectives and goals, and then we go to characteristics and needs, functions, use cases, and finally here you see the elements in the purple. And here you might start to recognize a few things. The ground system, space launch system, Orion spacecraft, these exist today. Human landing system is being worked on. Orion spacecraft exists. Deep Space Logistics Gateway, contracts are underway. The hardware is being designed. And so you can see that we're making progress, but we still have some things that don't exist yet. And remember that these are different segments. So NASA has a human lunar return is the first segment. That means you just get to the moon and you prove you can land, survive, and get home. That's what this is all about. Now you also have the humans to Mars, and that is the end state. So the end state is to get to Mars. You try to get to Mars by using the moon to learn and test all your equipment. So in 2022, NASA was focused on planning the architecture for human lunar return. In 23, NASA is focused on the architecture for humans to Mars, because that's the end state. And then in future iterations, we'll do foundational exploration, sustained lunar evolution. This is where the moon-based architecture gets defined. And you can see we're in 2023, we're not there yet. So this is still happening. And that's something we have to keep in mind. Here are the human lunar return segment elements, and those are also under work. Now here's something that shows the connection between Moon to Mars. And you can see all these different functions here and elements. And the one we're most interested in is probably in situ resource utilization, because that will allow our base to be sustainable. The robotics are also very important because our crew will not be there all the time in the beginning, and they won't be able to be in the radiation environment for too long before they've met their dosage limits. If you have more questions about this, you can use this tag here and go to this website. The architecture definition document is there. Moon to Mars architecture summary is there. White papers are there. So if you want to dive into detail on this, it's all publicly available. So, and these slides, I'll share these slides as well. So you can review those at your own leisure. Now, we in this community, we're most interested in the surface of the moon. And NASA has divided the surface of the moon up into these technology areas. Lunar Surface Innovation Initiative is the title. And for what I'll be talking about today is surface excavation and construction in the context of a lunar base. Doesn't mean the others aren't important. It's just that's what I'm focusing on to talk about how can we plan for building a lunar base infrastructure. We also have a group called the Excavation, Construction, and Outfitting Group. And this group is led by Dr. Mark Hilberger at NASA. And we've divided that into 4 functional areas: excavation for ISRU-based resource production. So without the excavation, without the regolith, the feedstock, you don't have anything. So in terms of resources. So that's the first step, is just excavating it. The second thing is regolith manipulation, site preparation. Well, you can't build anything without a foundation, and you have to prepare your site. It's the same thing as on Earth. If you go to a construction site, the first thing that happens is site preparation. Once you have your feedstocks and your site preparation, then you can get into construction. Once you've done construction, then you get into outfitting, where you actually put all the wiring and the plumbing and anything else you need into your structures. And then finally, the end goal for NASA is to have a commercial capability for sustainable infrastructure and economy. So the end state really is handing this off to industry, to commercial capabilities, so that the lunar base can be self-sustaining and can exist into the future without government support. Very quickly, we have class 1 structures, class 2 structures, class 3 structures. Class 1 is you bring it all from Earth. Class 2 is you bring it from Earth, but you deploy and assemble it. And class 3 is where you start to use some in situ derived components and to make your structures. Ideally, it would be 100% ISRU, 100% in situ derived materials and components, but that's a way out in the future. We're not there yet, although we are developing the technologies today to get there one day. If you look at this technology development portfolio, we've divided into go, land, live, and explore. And then those are the thrust areas. And then on the right, there's outcomes. And I've highlighted the live outcome. One of them is autonomous excavation, construction, and outfitting capabilities targeting landing pads, structures, habitable buildings using in situ resources. And those are all mapped to the taxonomy, the NASA taxonomy, which has various technology areas that NASA is developing. So this is a very structured framework. And in addition to that, we tie back to the architecture. So we go back to that Moon to Mars objectives document that I showed you earlier. It's called the Blueprint Objectives. And then we've taken the relevant objectives out of that document. And then we tie that to the different technology areas: regular excavation, delivery, manipulation, site prep, assembly, construction, outfitting. So now this is our stakeholder needs and goals and objectives. So that we're following the systems engineering process, and now we know what our stakeholders need, and we tie it to our different functional areas. Then furthermore, we take even a deeper dive and we go, okay, these are our functional areas, but what are the gaps? Because we have to invest in the gaps in order to get there. So we have a list of gaps, and those gaps are then tied to each functional area, and they're also tied to the taxonomy work breakdown structure. So this is all in a database at NASA called a Starport database. And it's internal for now, but in the future it will be publicly available for your review and your feedback and your use. If you want to write a proposal to NASA, this is a very good framework for communicating with NASA how you can help. So overall, we have internal roadmaps as well, and requirements are being developed internally, preliminary requirements. And we're investing in the technology development activities in order to increase what we call a TRL, which stands for technology readiness level. And you can't really fly until you're at TRL 6, which means you've tested your technology in a relevant environment. And then you might have flown once, you're at TRL 7. When you're operational, you're at TRL 9. So the goal is to become a technology that is operational at TRL 9, but it takes some investment and some due diligence in order to get the technology to that point. Now let's dive into the lunar surface. Well, let's talk about regolith as a resource. So we can use regolith in two ways. We can extract resources out of the regolith, for example, water, ice, other volatiles, or metals, iron, titanium, magnesium, calcium. So there's a lot of metals on the moon. And or we can use it as a raw material, as bulk regolith. Those are the two ways we can use the regolith. One nice thing about the moon is for 4.5 billion years, it's been just impacted by high energy impacts from meteorites, comets, these high energy events, and it's crushed the surface of the moon. And not only has it crushed it, it's ejected it. So this process of crushing and ejecting over large time spans is called gardening. And that's when the regolith is mixed and distributed over the surface of the moon. So you can see there's 10 to 20 meters of crushed rock, which is a very fine powder. Most of it's under 100 micron in particle size diameter. And so this is actually an opportunity because here on Earth, 5 to 7% of our energy on Earth is used to crushing rock to make concrete for infrastructure. So we don't have to crush rock. That saves us a lot of energy, a lot of logistics. We have a feedstock ready to go, which I call a construction aggregate. And I say basalt, but that's in the mare. Of course, in the highlands, we will have different kinds of minerals and orthosite. And so that's just an artifact of this being the Apollo program that I'm referencing. Now, the main thing we want to do when we get to the moon is have shelter. Shelter from radiation, shelter from micrometeoroids, shelter from thermal swings, and even the exhaust plume will have ejecta small particles traveling at 2,000 to 3,000 meters per second. So we just need protection from all this harsh environment. It's a very, very extreme environment, and we need to protect the crew, and we even need to protect the equipment. So that's a fundamental need. Now let's look at what would we require in a moon base. And here's a schematic that some of my colleagues made. It's a schematic of lunar base functional needs. And you can see the dotted line, the boundary here is the surface architecture. So we're talking about lunar surface only. We're not talking about transportation to the moon or landing on the moon, just the surface architecture. What would it take functionally for crew and robots to survive on the moon? And so when you start to look at a diagram like this, I think right away what you see is there are many functions, but almost as important is, or more importantly, is the interaction between all these functions and all the interfaces and how they work together. So this is actually an incredibly complex system that we're designing here. If we look at just pure infrastructure, we're talking about things like landing and launch function, lander servicing, propellants management, power, communication, habitation, life support, transportation, extreme access. That means going up and down steep slopes. Thermal management, extravehicular activity. That means a spacewalk. Food production, radiation protection, meteorite shielding, moonquake mitigation, science activity stations, resource mining utilization, regolith operations hauling, logistics management, excavation and construction services, dust management, maintenance, repair, and decommission, waste management, crew health. So there's a lot going on here. On top of that, you may want to have other things like I've listed here, things like dust mitigation, design for field repairability, long life systems. So there's a lot to think about when you're designing a lunar base. So first thing you do is you have to find a site. So when you find that site, you have to consider all of your subsystems, all of your elements, and then the interaction between these elements and the interaction between the environment. And the environment is as important as the other elements. So you may want to consider site location, the terrain, and geomorphology. So that can actually help you. There's many cases in human history where uh, indigenous people have burrowed into mountains to make caves and things like that. So the terrain can help you. It can also help you with radiation shielding if you pick the right location. Topography and contours, altitude, elevation, dimensions and area, climate, the space weather, lightness and darkness. These shadows are moving all the time at the poles. Albedo, that's the reflection of light off of the lunar surface. The radiation, both galactic cosmic rays and solar particle events. Wind flow, and that's only applicable to Mars where you have an atmosphere. Glare and reflection can really affect your cameras and your robotic systems, and spacecraft induced ejecta. So these are all dimensions of this problem that we're trying to solve. So on Earth, the architects, they start with something called master planning. And so there's a lot of definitions for master planning, but this is just a general definition. And I'll go to the last paragraph here. The ultimate aim of master planning is to create a holistic and well-considered framework that guides the development of large projects, ensuring harmony between buildings, open spaces, infrastructure, and the surrounding context while meeting the functional, social, environmental objectives. So a lot here. But the main thing is it's a holistically designed system with the human in mind. That's the main thing about master planning. So what does that look like? Well, usually in master planning, you have zones. And in the zones, you consider the interaction of these zones with the functionality and the environment and the usage and the humans. So this is just an example that Dr. Bob King and I laid out in a paper a while ago. And we just put down this a landing pad here, a landing pad here, roads connecting the landing pads, a central habitation zone with the first lander comes down, and you have solar power units and these other mobile power units, logistics area, ISU production modules. So you can see we're starting to just lay out these functional zones. And then in 1989, during the 90-day study, they had another concept, and there's many concepts out there. I'm sure you've seen them. But you can see that the basic idea of master planning is zoning. And so you have these launch landing facilities, crew habitation area, science area, you have transportation corridors or roads, and then you have ISRU area, which is where the resources are or close to where the resources are. You definitely need power. A base needs to be power rich to be robust and fault tolerant. Then you may have an astronomy array out there, a geophysical station. So you can see that this is all driven by what you're trying to do. Now let's talk about cautionary tales, because we should learn from history. Jamestown was established in 1607, and it's just a classic story in poor master planning. The initial location was low-lying and marshy, and they had malaria and all dysentery, all kinds of diseases and sanitation issues. They weren't self-sufficient because they hadn't planned for agriculture and growing food. So they started trading with the local indigenous population, and they became dependent on the Native Americans for their food. And that created some conflicts because the Native Americans weren't always on board with having them there. And there was poor leadership and internal conflicts. In the end, the location they chose just wasn't working. There was a lot of death, a lot of famine. And in 1610, they relocated Jamestown, but they still had problems. And they had significant loss of life. They had strained relations with Native American tribes. And so the whole thing really wasn't very well thought out. The only thing that saved Jamestown was this cash crop called tobacco. When tobacco became a cash crop, they were able to make enough money to actually keep it going. But this is a cautionary tale, number one. Cautionary tale number two is Seattle. An expedition went to Seattle, They went to Alki Point. They set up the Denny Party, set up in 1851. And then in 1852, the rest of the party came up. And the second part of the party said to the first part, this place is not a good place. It had poor soil for agriculture, lacked a deep harbor, lacked fresh water, inadequate transportation. So this second group that came said, no, we're moving to Elliott Bay. And that's where Seattle is today. So if you don't have the basics like water and agriculture and transportation, then your settlement and your city will not be successful. Master planning cautionary tale number 3 is closer to this time period, and it's about Antarctica. And you can see a lot of these stations were abandoned, and they were abandoned because they didn't pay attention to the environment, and the environment has drifting snow. So over the years, the snow and ice accumulation covered all these stations, and then they had to be abandoned. So you'll see the lesson learned was that the new stations are being designed with these actuators. So they're stilts that are actuated, and they actually jack up the stations and keep them from being buried in snow. But even that is not sustainable because one day this station will be covered. So really, it needs to be a jacking system that can jack itself up on top of the snow that accumulates. But that's still to be designed. Now, inside of NASA, we're using a work breakdown structure, and this is notional, but we realize that unless we get organized, then we can't really work on the elements and products and processes required for a lunar base. So if you're talking about just construction, then these are the functional areas that we're using and cataloging everything inside NASA for technology development. And if we have a solicitation or some kind of internal funding, then this is one way of organizing it. But I think it's useful, and I hope it's useful to the community, because now we can start to talk to each other in the same framework. And I think communication is a big part of this. Typical construction tasks are listed here, but you'll see there's a lot of infrastructure needs to be built. And how are we going to do this? How will we do this? Are robots going to do this? Will we bring the materials? Will we make the materials there? There's just a lot of work needs to be done, and a lot of technology development. In fact, I did a study on this a few years ago, and we always were under the impression that mining was really the main customer for regolith excavation. But in fact, when I looked at the Constellation program at that time, and we started laying out things like launch and landing pads, trenching, clearing, compacting, building berms, habitat shielding, turned out that 84% of the mass of regolith that we needed to excavate was for construction, and only 16% was for oxygen extraction for ISRU mining. So construction is the biggest customer of excavation, regolith excavation. Now, the other thing you might ask is, well, what kind of equipment should we be designing? Well, this was just another paper where I made an attempt to try to quantify that, and this is very notional, but if the exercise here was, if we're building and landing launch pads, what equipment do we need? Well, we need a cut fill excavator, we need a bulldozer, we need a regolith transporter, we need a grader, a compactor, and a paver. That's just notional, but you can see that's the exercises we have to go through using the systems engineering process, of course, but we need to start thinking about what kind of equipment should we be developing in order to build a lunar base. Now, some people are already thinking about this. For example, my colleagues at the U.S. Army Corps of Engineers, they have something they advertised recently called the Lunar Management Planning System. So they want to create a kind of a virtual environment with machine learning that will do site selection and assessment, infrastructure planning, resource allocation management, life support system, mission planning. All these things that need to be done can be done virtually before we ever go there. And these are the new tools. It's like a GIS, Geographic Information System. These are the new tools we have where we can actually do this before we ever go. So finally, I'd like to talk about a lunar mega project. And so over the last few years, I've been talking a lot to the civil engineering community here on Earth, mainly through the American Society of Civil Engineers and also through AIAA. But the main thing here is we're building a city on the moon. So first it will be a moon village, then a moon town, then a moon city, but eventually it will be civilization on the moon with a permanent presence, and then eventually Mars. So how do we do that? Well, my civil engineering colleagues told me, you're doing a mega project. So I said, what's a mega project? And they answered, look, it's a really big project. It's a large scale, complex venture that typically takes many years to develop and build, and it impacts millions of people. That's what a mega project is. It costs billions of dollars. Major project is hundreds of millions of dollars, and regular projects are millions and tens of millions of dollars in this context. So let's just calibrate our thinking. Apollo lunar program, if adjusted for inflation, would be $288 billion today. International Space Station, when it was all said and done, was about $150 billion. And then Space Launch System was about 17 billion, probably more by now. But this was a number I think I picked up in about 2020 or 2019. The Orion capsule has been about 16 billion so far. So these are big numbers. And when you're talking about big dollar amounts like that, it's a mega project. And if you say, well, if it's a mega project, how do we do mega projects? The civil engineering community, the construction community on Earth, they do this all the time. The Kashagan project in Kazakhstan, oil and gas, 116 billion. So that's on the order of what a space station costs. Then you have all these other natural gas facilities. Most of these are mining or oil and gas, but you can see they're in the billions range, and most of them above 10 billion. So we do this every day here on Earth. So then the next question was, well, if we do it every day here on Earth, how can we get dual use? How can we spin in and spin out things from terrestrial industry into the space industry and help each other? So we had a workshop at the AIAA Ascend conference in 2020, and we polled the audience there in the workshop with this app that summarizes the inputs, and the larger the font, the more responses were received. So the audience there thought that autonomy, additive construction, robotics, 3D printing, recycling, situational, these are the big topics where we can collaborate with terrestrial industry. So the big takeaway here is automation. If we have robotics and automation, now we can start really collaborating with terrestrial industry, because they're interested in that for their terrestrial projects as well, especially given the labor shortage which we're currently experiencing in the construction sector. So the next thing that the construction industry told me was, you have to think about the contracting mechanisms, because these are big projects. And so usually it's a consortium that bids on this. It's not just one company, it's a consortium of companies, or it might be a public-private partnership, but there are many mechanisms for doing this. And so these are some examples of how to do it. And then at NASA, we always talk about public-private partnership because it's a good deal for NASA. It's private money, and with an investment from NASA, a matching investment from NASA, and then we go do it. When I talked to private industry, they said, no, we don't like public-private partnerships. It's too much risk. We can't take that risk. And we don't have any guarantee of income. And so I thought that was a pretty interesting comment from them. And they were actually more in favor of build, own, operate, and transfer, or the design, bid, build, or building it and then operating it, and having a government agencies as an anchor tenant with a guaranteed contract. So we really have to pay attention to what industry wants, or they won't bid. If it's not attractive to them, they won't bid on these mega projects. And so you can have a joint venture, limited partnership, or consortium. So this is something we don't talk about much at NASA, but the business world does. So we need to pay attention to it. Then I also realized that we were talking in different languages, different vocabularies. So here's a little crosswalk showing if we talk about PDR, which we talk about all the time in the space industry, and CDR, and we talk to somebody in the construction industry, they don't know what we're talking about. They would call that a PEP or an EEP, engineering execution plan, or project execution plan. So if we don't talk the same language, we're not going to be able to work together. When we get to CDR, which is our 90% designer view, where we're ready to go in the systems engineering process, ready to go build, they call that the construction execution plan. So unless we speak the same language, we're never going to be able to work together. And so that was the intent of this paper, was to publish a lexicon for translating the terminology. And then also, this is how we work at NASA. This is our life cycle. Well, in the construction industry, they have different terminology. They have concept, pre-feasibility, feasibility. So if I say I'm working over here in pre-phase A, so that's the concept part of the systems engineering process at NASA. It's called pre-phase A or concept study. Well, they call that concept study. But if we say pre-phase A, then they won't know what we're talking about. So again, we have to pay attention to vocabulary. All right, I understand we want to have some questions, so I did go through this very quickly, but hopefully it stimulated some thinking on your side. In summary, I talked about the NASA program planning process, the Artemis phases. If you're wondering what's going on inside Artemis, hopefully I answered your questions there and you know where we are in the planning process. Then I talked about the NASA systems engineering methods. Like I said, that's the secret sauce of NASA. If you can do NASA systems engineering, then you can do very, very complex projects. And that includes a mega project. And so then I talked about previous NASA space mission architecture studies and how we've been doing this for a long time, but we've never actually gotten there. And the reason why is because we haven't had all the stakeholders lined up, but we seem to be doing that now. So it's a very good chance that we will be building a lunar base very soon. And then once we have all the stakeholders lined up and everybody's in agreement, then we can do the functional analysis of a lunar base. We can start classifying the infrastructure, lay out our WBS. And then once we have all our structure, our framework for how we can talk to each other, how we can fund this, how we can work with each other, including industry, then we can start master planning and site layout. And in the master planning process, the human element is very important because you're planning a community. So the community has to be holistically designed to be functional. It has to be a nice place to live. It's one way of looking at master planning. Let's make a nice place to live. And then program management is different in the space industry compared to the construction industry. We need to pay attention to that. The construction industry is ready to go build a moon base, but if we don't issue a solicitation in a language and a contracting structure that they can understand and accept the risk, then they won't get involved. And finally, mega projects. This is nothing new. NEOM in Saudi Arabia is being built right now. That's a huge project. It's in the billions of dollars. This is nothing new. We do mega projects all the time, and we can do this on the moon. And so finally, I think that we can do the technology development and lunar base construction, and it's going to require a common framework, and it's going to require international teams and consortia because it's such a big project that we have to spread the cost and also get the best minds in the world working on this. We're going to need some real intellectual horsepower here. And if we can pull all that together in a good framework that everybody understands, and everybody understands the rules and how we work, then we can make this happen. Thanks, and I'll be happy to answer any questions now.
Hi, Rob. First off, great talk. So with that, I will open to the Q&A. So first, Alice Nohel asks, will the recording be available? That one's for me. Yes, it will, everybody. We're working on getting the access to YouTube to upload these as part of the AIAA Space Resources Technical Committee. Miguel Cotto says, Rob, You might want to look into IPD, Integrated Project Delivery. This method has been very successful for their projects their company has done in the past decade. So for what that's worth.
Yeah, thanks, Miguel. That's why we are having this discussion, is to get feedback from everybody in the construction industry. I know you're in the construction industry, and thank you for your advice.
Awesome. Thanks, Rob. Alice Noel once again says, wonderful presentation. Love the future opening of the database and the lexicon work. Is any exploration on biotech involvement to create designer ecosystems for low G environments? Is any of that kind of stuff going on?
So I'm trying to understand what biotech means. If you mean biotech to create construction materials, I know of work going on at Stanford University for synthetic biology and at Ames Research Center for synthetic biology to create binders for lunar concrete, if that's what you mean biotech. If you mean biotech like life support systems, recently on the International Space Station, they achieved a 98% closure loop for the environment control and life support system, ECOLIS. So we're making progress to 100% closed loop ECOLIS systems, but that's about all I know about that.
Awesome. Thanks, Rob. Patrick Sewerman says, I just got back from the Moon to Mars workshop in DC yesterday. It seems like they've not spoken to you, Rob, because your valuable information was sorely missing from their M2M architecture development project.
Okay, Patrick, thanks for your comment, but I did point out that we're in the early stages of this. And if Spuds was there, he will have told you that please be patient. And the whole team is working very hard inside of NASA, but they do ask for our patience because this is a very structured process and we're not there yet. We're not on the lunar surface yet. They're just trying to get to the point where we can deliver astronauts safely and routinely to the surface. And they haven't gotten to this point yet of infrastructure planning and development. I know we all want to do this, but our management has very clearly asked us to be patient and to follow the process. And that's why I wanted to show the process to you today, so that you understand the process and that we're doing a disciplined, rigorous systems engineering design here. And we need to follow that process, and it takes time. So that's all I can say, is they've asked us to be patient.
Well said, Rob. So Catherine Wachoff asks, how is NASA considering return on investment for lunar and Martian bases as it chooses site locations and begins master planning? You mentioned public-private partnerships are not interesting for the construction and private industry partners for cost reasons. So how is NASA thinking of the profit of the future lunar infrastructure as an incentive for getting industry involved?
Okay, so that's a really good question, because NASA doesn't measure its shareholder value like a private company does. We don't issue stock. We don't have a price to earnings ratio. We don't have all those things that you have in private industry, where you can measure the metrics of financial performance of a company. The government doesn't work that way. The government works in the public interest, and the public interest is much more nebulous than a financial metric. It's for the public good. And so we have a lot of criteria to measure what is the public good. But the main criteria that NASA uses for success is science. So science value, science return. That's the main metric for success. If we advance the state of knowledge in our solar system, in our universe, then we have been successful for the human race. So it's not something you can measure in dollars. And that's where the struggle is. But we do need to make it attractive to these private industry. And that's where we need private industry to come in and tell us how we should structure it, because we're not the experts on that. Private industry needs to come in and tell the government how we should structure the solicitations so that they will actually bid on them.
Interesting. I didn't know that. Thank you, Rob. So Patrick Sewerman asks, can you shed some light on how the SwampWorks team is informing the administrators?
So we have something called principal technologists, and the principal technologist is the lead for that technology area. And in our case, for excavation, construction, and outfitting, it's Dr. Mark Hilberger. So I'm on a team of leads that we report to Dr. Mark Hilberger, and then he goes and reports to the Space Technology Mission Directorate, and the Space Technology Mission Directorate reports to NASA headquarters to the administrator. So it's a structured organizational process, and we we go up and down the chain of command.
Excellent. And Nicholas Bellato asks, what are good avenues for PhD students or university laboratories to propose research in the area of site preparation and construction?
We have a lot of very good support for academia. We have the fellowship program. A PhD student can apply for a NASA fellowship. So that's probably your best bet if you're a PhD student, but it is highly competitive. So you have to really compete for that. Now, the other thing is we have the Big Ideas Challenge, where university teams can respond to we have a different challenge every year for the NASA Big Ideas Challenge. That's a good one too. We have the EPSCoR program, where minority institutions and disadvantaged institutions can apply for NASA grants. And so that's out there as well. We have the STTR program, which is where a university partners with a small company and bids on a contract, and we have a solicitation that comes out every year. And so that's a really good way to get funding too. You get a phase one for 150K, phase two is 850K, so $1 million total funding if you make it through phase one and phase two. So I would encourage you just to go online and look at all the different funding mechanisms. I know it's kind of complicated, but the funding sources are out there, and if you need help, you can reach out to NASA. They have program people that can help you with that.
Awesome. I think we have time for one more quick one. Then I just want to do a couple quick announcements before we close. So Chris Peterson asks, any thoughts about a base on pyroclastic deposits?
Well, that's part of the whole site survey. We need to understand what we're working with before we make a decision on where we're going to actually put the base, and you know that needs to be well studied. So the geology of the area needs to be studied, but the moon is covered by regolith. So you know, people that say they want to build a moon on bedrock, well, there may be outcrops of bedrock, there may not in the place we want to go. So really, that's part of the whole site survey process, and we just have to go through that process, evaluate it, and then just make a decision.
Okay, perfect. And we're at the top of the hour. So first off, again, thank you, Rob. Excellent presentation. I really appreciate your time on behalf of the AIAA Space Resources Technical Committee. Thank you, everyone, for all of your questions. This recording will be available on YouTube, and the slides will be available on the AIAA Engage website. There is a public-facing part of this where I will upload these. You do not need to be a paid member of AIAA. You do need to make an account for AIAA Engage, but again, you do not have to pay AIAA dues or anything like that. So with that, if anyone has any other questions, please feel free to reach out to me. And again, thanks, Rob, and thank you everybody else for a wonderful time. I'll send out the announcement for the next month's webinar shortly, so keep an eye out for that on various platforms. Thanks, everybody, and have a great rest of your day. Bye.